what I want to talk about is based on my PhD research at the University of Toronto with Marco Gualtieri. The plan is to go over these things called Lie groupoids, which are sort of generalizations of Lie groups, talk about these things called Morita, equivalences between them. Then using that, we'll construct these things called Picard groups and look at examples from Picard groups coming from holomorphic Poisson geometry. So I have not a great idea of the background of everyone here. So if you want to ask a question, don't hesitate. Happy to explain more. Okay, so for us, the basic object is going to be this thing called a Lie groupoid. And a Lie groupoid is just a groupoid object in the category of smooth manifolds. So for those of you that don't know, a category is a thing which has objects, dots, and arrows between those dots, and it's called a groupoid if every arrow has an inverse arrow. Okay, so it's a category with invertible morphisms.
It's an internal category.
This is internal category in manifolds.
Okay.
Yeah. So what that means is that we have a manifold of arrows. The arrows of the category form a manifold. The objects of the category also form a manifold. And there's two maps from the arrows to the objects, which just take an arrow and it sends it to the source of the arrow. So if this is X and this is Y, this would be source of G, and then Y would be the target of G.
So like each map has a map to its source and target.
Each So there's a manifold of arrows, and then there's a map from arrows to objects, which takes an arrow to the object at its source and the object at its tip. Yeah. Then the additional piece of data you need in a category is the multiplication, which takes a pair of compole arrows. So this E2, these are just the pairs of arrows which you can compose in the category, and it sends it to their composition. So G and H will be mapped via M to G composed with H. So, and then the last thing we need is this embedding of the units via the identity arrow. Okay, so let's go over a bunch of examples. A very important example is Lie groups. So if you have a group G, there's a way of thinking about it. So this is a group. You can think about it as a category with a single object, and then the group elements form the arrows of that category. And if G is a Lie group, then this category that you build out of it is going to be a Lie groupoid if you just look at the axioms. Okay, so if your objects are just a single point, then a Lie groupoid is just a Lie group. So in general, a Lie groupoid is going to be like a generalization of a Lie group where we have many objects. Yeah.
Is it possible to just take a Lie group?
Yeah.
And then just forget the totality?
Totality.
Closure under you just don't have closure under
like composition.
Well, maybe it's commutativity.
We don't need anything like that. No.
Okay.
No, so we're just thinking that like here's I'm going to build a category where there's a single object, which is this point, and then there's a bunch of arrows here, and these arrows are all invertible, so they have like inverses, and those arrows form a group, and that's exactly what a Lie group is.
Yes, yeah, sure. But a groupoid is not.
Yes, so let's see a few more examples. Here's another groupoid. Well, there's like a variable flag when I move to the screen. So if X is any manifold, then we can build this thing called the pair groupoid. So its space of arrows is going to be X times X, and its space of objects is just going to be X. Okay. So I think of an arrow here as just, this is like X1, X0, and its source is X0, its target is X1. And if I have, X1, X0, X2, X1, then I can just, oh no. I don't know what happened. Oh, it seems my screen sharing stopped. Sorry, 1 second here. Okay, that was unexpected. And we are back. Okay, we're back.
Can you also share?
Yeah. Okay, great. So in this case, multiplication is just given by concatenation of these pairs. And the units sending an object to the identity arrows, just sending it to x times x, or xx. So you could pick this as being some space here. The groupoid is like x times x. And then there's this identity, which is just the diagonal of x. And every element in here has a source. This is, say, G. Then I can send it to its source and its target. Okay. A related example is if you have any manifold, you can build its fundamental groupoid. So this is a lot like the fundamental group. So in this case, the objects are again just going to be the space X, but the arrows are going to be smooth paths in X, where I'm going to look at homotopy classes of these paths modulo endpoints. So you literally just have now some path in X, gamma, and the source is just going to be evaluation at 0, and the target map is going to be evaluation at 1. And then multiplication is just given by concatenation of paths. Okay. Any questions about these examples? Okay. So there are plenty of other examples coming from functions. If you have bundles of Lie groups, Lie group actions on manifolds, these things called Stokes groupoids. Okay, but if we want to think of a groupoid as being a generalization of a group, then we can ask what properties of groups, what things can you do with groups, can you generalize to Lie groupoids? So we like having groups act on things, and we can have groupoids act on things as well. So if I want a groupoid G to act on a manifold P, I need to specify some data. The first thing I need to do is specify this map mu called the moment map, which is going to map P into the space of objects of the groupoid. And then there's an action map, which is going to let arrows in G act on elements of P if the source of an arrow agrees with wherever that point P lands in mu. So this is saying that G acting on P is defined if and only if the source of G is equal to mu of P. Okay, I can't just act on an arbitrary element of P with an arbitrary element of G. That's not allowed. And if I can do this, then after I act on G with P, it needs to end up at the target of G if I apply the moment map again. And it should be a module action. Okay. So, all right, so that's probably the hardest definition. If we have now a map from P to B, this doesn't need to be a surjective subversion or anything like that, but a left G bundle now is going to be just a space P with a map to B, and I want this map to be invariant under the left G action. Okay, so just like a G bundle, has an action of G on it, and the projection map should be invariant. I'm asking the exact same thing here. And such a G bundle is going to be called principal if we have this condition here, which generalizes the principality condition for principal group bundles. So what this is saying is if I ever have a pair G and P where I can act on G by P, then I can get anything in P's fiber by acting on it with something in G. So this is a bit weird to look at in formulas. I'll draw a picture here instead. So here's my groupoid G. These are like the arrows. Then here's G0. These are the objects. And there's like an embedding of the G0 inside of G1. Okay, now here's my space P. I'll draw it a bit bigger. All right. So what's happening is I pick some point P, and it's got its image down here, which is mu of P. Right? This is where it goes under the moment map. Now, okay, so here's mu of P, thinking of G naught embedded inside of G1. If I pick some groupoid element here, whose source is equal to this, okay, so the source of G is equal to mu of P, then when I act on this P by G, I'll get something up here, which is like G acting on P. Okay, so I'm just acting on the space P using this groupoid element G. Now, because this map pi down to the base is equivariant, I know that everything in this line here, which maybe I'll change colors, everything in this line here, which is the fiber over this point P, say, G acting on P and P are actually going to map to the same point, right? That was one of the bundle conditions. And what this principality condition is saying is that I can get anything in this fiber from a unique thing in this fiber over here. So it's saying that I can identify this red fiber in P with this red fiber in the space of arrows, G. Okay. So the example that we're probably familiar with is principal Lie group bundles. If your groupoid is just a Lie group, then a left principal G groupoid bundle is just the same thing as a principal G bundle that you study in your differential geometry class. Okay. And in that case, you have for every B in B, we know that pi inverse of B is just a copy of the group G. This is what we're used to for a principal G bundle. Okay. The thing that's changing now when we go to groupoids is that as I change this point B around, so if I pick some other point here, this fiber may not look like the red fiber anymore. It's going to look like some other fiber in the groupoid. Okay. So what's happening is fibers of this pi map are going to look like source fibers in the groupoid. And as I change around my point in B, I'm going to get different source fibers, and these can look different. It's not constant like a single group everywhere. All right. Okay, so that's the notion of a principal G bundle. Oops. Wow. Just waiting for it. Okay, there we go. So now we're going to do something which is inspired by this notion of Morita equivalence from algebra. So in algebra, there's these things called Morita bimodules. So you have two rings and then R and S, and you want to tensor on the left and right by this bimodule. So what we're going to do here is replace these things by spaces. And we're going to have some space P now with a left G action and a right H action. So P is going to be called a GH Morita equivalence if it's a bi-principal GH bi bundle. So that's a very long name, but all that means is that if I forget about this H1, then this is now a left principal G bundle. Okay, this thing we were just looking at. And if I were to forget that G0 was the base of some groupoid G, then this should also be a right principal H bundle. I didn't tell you what a right action is, but if you know what a left action is, you can maybe guess what the right action is. And we want the G and H actions on this space to commute with one another. Okay. So way you can think about this is, yeah, it's like a bimodule from algebra. Okay, so that was a lot of data. You can ask, do these things ever exist? And for every groupoid, there's a canonical Morita equivalence. So we can just take a space of arrows of groupoid, and this is going to be a Morita equivalent to it. So why is this true? Let's pick some G in G1. Okay, Now what I need to do is specify a left action. Okay. So if I have some arrow in G1 whose source is the target of this G, then I need to get something else in G1. And how am I going to do that? Well, I can just post-compose. So in this case, the left action is just given by categorical, like post-composition. And the right action is just categorical pre-composition. Okay. So those are the left and right actions. And then what the principality condition is saying here is if I have G in G1, let's say it maps to X in G0. Now what I need to do is take S inverse of X. So these are all of the arrows coming out of X. And I need to identify this with S inverse of T of G. Okay. And there's an obvious map here, which is just left multiplication by G. Okay. So this is sort of the canonical example. If we have a discrete group, we can try to classify all of its Morita self-equivalences. Okay. So this is just a discrete group now, thought of as a groupoid over a single point. And to begin with, we can split this left action, or this left moment map, by which I mean just pick some point P naught E. Okay. Now, if I do that, I'm going to get an isomorphism of G with P, where I'll just send a group element G to G acting on this P naught. So this P naught is sort of functioning like an identity element. This is like this fact if you have a principal G bundle for GLE group and you pick some like a section of the bundle everywhere, then it trivializes the bundle. This is what we're doing. Okay, so by using up the information in the left action, I get this trivialization, but then there's this residual right action. And you can check from the axioms that this right action is going to give us an automorphism of this group. Okay, so if you just have a group as your groupoid, then Morita auto-equivalences, so self-equivalences like this, are in one-to-one correspondence with automorphisms of the group. Okay, so you can think of these as being generalized symmetries. So in this case, for the group, we've seen that these correspond to automorphisms, and for a general Lie groupoid, they're sort of like the Lie groupoid version of an automorphism.
What do you mean by that? Because like you're gonna have many more of these things, like because P can be like there'll be a class of such things, so you have to have some equivalence between. What's the equivalence between the automorphisms?
We'll get to that in about 10 slides. Yeah,
That's to make sense of that. You need to do that. Is that correct?
Yeah, so there's going to be like a further notion of equivalence between these bibundles. But if
what
you
I mean is that statement is up to equivalence between the bibundles, I guess.
This one, Morita autoequivalences? No, this is just before we take the equivalence. If we impose a notion of equivalence between bibundles, we'll be getting some quotient of G.
But I guess this is after you've chosen the trivialization.
Oh, after choosing the trivialization. Yeah, that's true.
So this is for
I see what you mean.
fixed P that you're doing. P's fixed.
Yeah, that's right.
Because you have the class of P, right? You can have like.
Yeah, that's right. That's right.
And I think it's like P with
Oh, if you take P with the splitting.
and then you might as well.
Yeah, that's right. So this is Morita
Fix it
autoequivalences
one particular.
with yeah, good point. With P naught in P. Yeah. Yeah, that's a good catch. Okay, so I personally think this is the most illuminating example of what a Morita equivalence is. We saw, okay, so let's say that X is a path connected manifold now and pick some point in it. Then we can consider in the fundamental groupoid, which is, remember, this space of paths up to homotopies relative to the endpoints. We can consider the source fiber of a point. And this is just going to be all homotopy classes of paths which start at this point X, which is like a model for the universal cover of X. Okay, then I'm claiming that this source fiber is a Morita equivalence between the fundamental groupoid of X and the fundamental group of X based at this point. Okay, so why is this true? Let's pick some path here, gamma, and let's say this is gamma of 0, this is X. Okay, so there's a left action which is just saying that if I have a path which starts at gamma of 1, well, the left action is just going to be given by post-composition again. Right? I'll get a new path which starts at x by just moving along this entire line. Okay. And then there's a right action here, which is saying if I have a loop based at x, I can just pre-compose with this loop, and I'll get another loop based at x, where now I'll go like around the loop, and then I'll follow my original path. Okay. And both of these actions are principal. So this is saying that the fundamental groupoid is Morita equivalent to the fundamental group of x based at any point. All right.
You mean the fundamental group, like large or low sum kind of, like you're taking all loops, but you mod out by smooth reparameterizations?
I guess so. This is just like the usual fundamental group from like in Hatcher, for example.
Oh, so it's like a set, it's a discrete set.
I guess I'm thinking of it as a group. Sure, yeah, as a set, that's fine.
Group, but I mean it's discrete. It's not
a
manifold, it's a discrete manifold.
Yeah, that's right. I'm thinking of it as a zero-dimensional manifold. Yeah, that's right. Okay, so we have groupoids, and we have this notion of Morita equivalence between groupoids. So you can ask if you're a categorically minded person, how do all these things fit together? And the theorem, which is like a folklore theorem, I think, the only place I've seen a proof is in this paper of Christian Bloman, says that Lie groupoids with Morita equivalences as morphisms between them form a special kind of category called a two-groupoid. And I'm going to denote this two-groupoid by ST-man. This word groupoid here, you should not really think of it as being like super related to the notion of a Lie groupoid, really. I'm not saying that Lie groupoids, the collection of all such things, forms Lie groupoid again. I don't think anything close to that is being true. But what this is saying is the following. In a category, I said we have dots, which are the objects. We've got morphisms between them. But in a two-category groupoid, you have a bit more structure, which is if you have two morphisms, G and H, then I can talk about morphisms between the morphisms. So there's a Hom space, G, Hom, G, H, where every G and H which go between the same pairs of objects. Okay, so what I'm going to tell you now, I've told you what the objects of this thing are. I've told you what the one morphisms are for Morita equivalences. I'm going to tell you, first of all, how to compose morphisms, and then what the two morphisms are. Okay. So let's do composition of one morphisms or Morita equivalences first. Okay, so if I have three Lie groupoids now, G, H, and K, and I've got a Morita equivalent from G to H and a Morita equivalence from H to K, then symbol P star Q by doing the following thing. I'll take P fibered with Q over the space of arrows of H and then quotient out by H1. So that is this diagram. I'm going to take the fiber product of P with Q over top of H naught. So taking pairs of elements P and Q, which map to the same thing in H naught. And then both of these spaces have an H1 action. So I'm going to quotient by this diagonal H1 action. Okay. And this resulting space has a residual left G action, both of which are principals. So this is now a Morita equivalence from G to K. Okay, so this is my composition in this category. This is the composition of one morphism. Questions about that? Okay, cool. Now I'll tell you what the two morphisms are. If you have
sorry, I did have stuff.
Yeah.
So we quotient out on H1, that's like something or something like that. Like you're not pushing, it's like H1 is like a group that acts kind of.
Yeah, I guess I'm imposing like a smooth equivalence relation on the points in this manifold. But because of the principality assumptions, everything that you do here preserves the fact that you're still a smooth manifold. But yeah, H1 isn't a group. It's just a way of identifying points with one another. Yeah. Okay, so now if I have two morphisms, if I have two Morita equivalences P and Q between the same two Lie groupoids, G and H, then a two morphism is going to be a different these thought of as manifolds, but it should commute with all of the actions. So the left G actions and the right H actions. Okay. All right. So with this setup, we can define like the main object, which is this Picard 2 group. So if you fix the Lie groupoid G, its Picard 2 group is the automorphism 2 group of G thought of as an object of this 2 category. So what that means very concretely is the following. A 2 group is like, okay, before we said a group was a category with a single object, and all morphisms are invertible. So 2 group is like the same thing, except that if I have G, a group element, and I have H, a group element, then I can talk about morphisms between my group elements. It's like a weird group where for every 2 pairs of group elements, you can have a Hom space between them. Okay. So the group elements of this Picard 2 group are going to be Morita autoequivalences, these things we've been looking at. And the 2 morphisms are going to be these bi-equivariant diffeomorphisms we were looking at again. And then the composition is the composition we just discussed. Okay, now the Picard group, which is a genuine group, is going to be the associated 1 group, which is saying that if you have 2 of these bibundles P and Q, and if there's a single 2 morphism between them, then I'm going to identify them. I'm going to like impose an equivalence relation on bibundles where they are equivalent if there exists some bi-equivariant diffeomorphism between them. Okay. So if this was G1 and G0 and G1, then this P would be equal to this Q in the Picard 1 group of G, because there are 2 morphisms between them. Okay, and that's an actual group. All right, so let's go back to this example of discrete groups. So we saw that if you have, just waiting on it. There we go. G, then the 1 morphisms or Morita autoequivalences of G, thought of as a Lie groupoid, are in correspondence with automorphisms of G. Now, if you have 2 Morita equivalences, you can check that the space of 2 morphisms between these is going to be a copy of the group. And when you translate that through this morphism, this is saying that I should consider 2 automorphisms to be equivalent if they differ by an inner automorphism. Okay. So what this is saying is that the associated 1 group is going to be aught mod in aught.
I think you meant the homomorphisms from P to anything else is G.
Isn't that what I wrote?
So I think there might not, like not all P and Q are equivalent.
Sure, yeah. Yeah, so if the space of 2 morphisms, if there are 2 morphisms between is a copy of the group G. I guess, like, I'm just saying, you can ask when are these automorphisms equivalent under this notion of 2 morphism I just gave. And this is given by a map from G into automorphisms of G, which is sending a group to its conjugation automorphism.
There might always be an automorphism to the case of a discrete. Or there's not.
Well, there's not all.
Even for,
I think you had a good assumption on the previous slide.
Yeah, so I'm saying if there.
If it's not empty, G.
Yeah. So this is G or.
But I think like from P to P, it's going to be only the elements of G which commute. Like
So for the things from G to G, that'll be like pi2 of the two groups. That'll be like the center in this
Exactly.
case.
So it's
Yeah.
not going to be just G.
Sure. Okay. So in
It's like
Q not equal to P, I guess.
I think it's like P blank. G.
P blank. G. Okay. So this might be slightly imprecise, but I propose we move on from that. What is definitely
One
true.
side is acting on that, one side, when move it to the other side inverse, so. See why it has to be central.
Yeah. Maybe let's talk about this afterwards. Okay, but if we buy that, then we can now already do a computation for a really interesting groupoid, which is saying that the Picard 1 group of the fundamental groupoid of a space, if it's path connected, is just the outer automorphism group of pi1 for any x in x. And this is really easy to see now. We saw before that the fundamental groupoid is Morita equivalent to the fundamental group based at x. So that means they have to have equivalent Picard 2 groups and 1 groups, because the Picard group is a fundamentally Morita equivalent invariant notion. So because these are Morita equivalent, they have Morita equivalent Picard 1 groups, and we just calculated the Picard 1 group of that because that's a discrete group. Okay. All right, so there is a big examples. Okay. Now to completely change gears and talk about some examples coming from holomorphic Poisson geometry. So those of you who don't know, a holomorphic Poisson manifold is a complex manifold X. So it's like a manifold, but instead of looking like real Euclidean space, it looks like C to the n for some n, together with some global holomorphic bivector field. So this is something which locally looks like it's a wedge of 2 vector fields, whose associated Poisson bracket satisfies the Jacobi identity. Okay. So Poisson manifolds, this bivector allows you to define a Lie algebra structure on the space of functions of that manifold. All right, so there's lots of examples. The example 0 is you can take X with the 0 Poisson structure. That's a perfectly good Poisson manifold. Another example is if you have a holomorphic symplectic manifold. So omega here is some closed 2 form, then which is not degenerate. Then you can invert the 2 form, get a bivector field, and that is now a holomorphic Poisson manifold, where you can match up the integrability conditions. So this form is closed exactly when this bracket satisfies the Jacobi identity. If we are on projective space, so say P2, then wedge 2 of the tangent bundle is going to look like O3. This is the line bundle of like cubic polynomials in 3 variables. And this means that a holomorphic Poisson structure is going to be determined by some cubic in P2. Okay, and on arbitrary projective space, we have these toric Poisson structures written in local coordinates. This is the bivector. So here's the wedge at the 2 derivations, and the coefficient of this is going to be Zi times Zj with this lambda ij, and this lambda ij can be any skew symmetric matrix with complex values. And this defines a Poisson structure on Pn. Okay, so Poisson structures are examples of these things, or give examples of these things called Lie algebroids. So a Lie algebroid is something which wants to be the tangent bundle. And the reason it wants to be the tangent bundle is because it consists of a holomorphic vector bundle and on its sections. So just like there's a Lie bracket on vector fields on a manifold, but it isn't the tangent bundle. It's just related to the tangent bundle in the sense that there's a map from this Lie algebra on sections to the tangent bundle, and this has to be a Lie algebra morphism. So the most basic example is if you just pick E to actually be the tangent bundle, will just the identity. Then this is an example of a Lie algebra. Okay, but the example that the only one we really care about today is a holomorphic Poisson structure gives us a canonical Lie algebroid. So a holomorphic Poisson structure turns the cotangent bundle into a Lie algebroid. So if this is true, I need to tell you what the anchor map is. This is a map now from the cotangent bundle to the tangent bundle, and it's just going to one form to the vector for which I get by contracting that one form into the bivector. Okay. And then there's a formula for the Lie bracket. This formula doesn't really matter. Just maybe you couldn't think of what the Lie bracket should be off the top of your head. There's a formula for it. Okay. Now the terminology is maybe suggestive. We have Lie groups and Lie algebras, and we have Lie groupoids and Lie algebroids. So we've added the same suffix to the same set of words. So you should, if you're reasonable, maybe you think that they're related to one another, and they definitely are. If you have a Lie groupoid, then you'll get a Lie algebroid, which I just denote by Lie G, on its space of objects, which as a vector bundle, I just take this anchor map. I look at all of the vector fields on the space of arrows, which are tangent to these target fibers. Sorry, I said anchor map. So I look at vector fields which are tangent to the target map, and then I just restrict those to G. The details of this aren't super important. It's just that you should know that there's a differentiation functor, which takes Lie groupoids to Lie algebroids. And we're going to say that a Lie algebroid is integrable if it's in the image of this functor. So if there is some Lie groupoid G where A is Lie of G. Okay. In this case, we'll say that the Lie groupoid integrates the Lie algebroid. And you might say, well, what's the point of this definition? Because shouldn't all Lie algebroids integrate to a Lie groupoid, just like for Lie groups? This isn't the case. There are examples of Lie algebroids which do not come from a Lie groupoid like this. You'll probably never see one, but they do exist. So an example is a Lie algebroid is, sorry, a Lie algebra is just a Lie algebroid over a point. So why is this? It's a vector space or a holomorphic vector bundle over a point. So that is a complex vector space. And it needs to have a map to the tangent bundle of a point, which is just the zero vector space. So there's no data there, and it needs to have a Lie bracket on G. So if you have a Lie algebroid over a point, that's just a Lie algebra. And Lie's third theorem tells us that all of these are integrable. We can always find a Lie group or Lie groupoid which integrates them. Okay, so now what I'm going to do is I'm going to assume that I have some holomorphic Poisson manifold, which is integrable, which, oh no, what happened again?
Looks like it just changed desktops. You can shift it back over.
It changed desktop.
I'm not sure. I'm used to Linux, but it does things.
I think it's
Yeah, they might be this turn.
my program here. I don't know why it keeps cutting out. This is strange. Yeah, I mean, I teach with this and this doesn't usually happen. Okay. We're back. Okay, so yeah, what I'm going to do is I told you that we have these things called holomorphic Poisson manifolds. They're like manifolds with some geometric structure on them. And they give you this thing called a Lie algebroid. And what I'm going to do is assume that this associated Lie algebroid on T star X, I'm going to assume that it's integrable, meaning that it comes from some Lie groupoid. Okay, so in other words, I'm going to assume that this Poisson manifold is now the base, like the space of objects of some Lie groupoid. And if this is true, then these Lie groupoids are actually very special and interesting objects. So if G, this G here, is the source simply connected, some technical adjective, Lie groupoid which integrates a holomorphic Poisson manifold, then it's automatic that this G itself is a holomorphic Lie groupoid, which if we think back to the definition of Lie groupoid, just that definition where with the definition where everything's a complex manifold and all maps are holomorphic. Furthermore, this holomorphic Lie groupoid carries a canonical holomorphic symplectic structure. So this is going to be a closed non-degenerate 2 form on the space of arrows, holomorphic. And this is a special holomorphic symplectic structure because it's multiplicative, which means it satisfies this condition here, which maybe I won't go into in too much detail, but what this is saying is it defines this thing called a one-shifted symplectic structure. That's what this last condition is saying. So of the groupoids, and in particular, they're holomorphic symplectic. Okay, so now what I'm going to do is if I have 2 holomorphic symplectic Lie groupoids, which I can think of as integrating holomorphic Poisson manifolds, I need to upgrade this notion of Morita equivalence to account for this extra data. So a holomorphic symplectic Morita equivalence now is going to be a diagram like this, where P now isn't just a smooth manifold, it's a holomorphic symplectic manifold, which is a holomorphic Morita equivalence between G and H, if you just forget about the symplectic structures for a second, which just means all structure maps are holomorphic. And I need to account for the symplectic structures too. The left and right actions both need to be symplectic, which is this technical condition here. Okay, so these are the kinds of Morita equivalences we're going to be looking at now. Okay. So the main object of the talk then is if you have a holomorphic Poisson manifold, which integrates to this symplectic groupoid, its Picard 2 group, denoted by Pic X sigma, is the same 2 group that we constructed before. It's the 2 group where the group elements are these holomorphic symplectic G omega Morita autoequivalences. So diagrams like this, where this is now G omega G, and this is G0, which is X sigma. Okay, so there are things like this. These are my group elements. I can compose group elements exactly like I did before, and my 2 morphisms are going to be exactly like they were before, except now they're also just going to be holomorphic and respect this symplectic structure. Okay, so this Picard group is, or this 2 group is exactly like the previous 2 group, except that now we just have to take into account the holomorphic and symplectic structures. Okay, so an example, if you have a holomorphic symplectic manifold, then we have this anchor map for this cotangent Lie algebroid, which took a 1 form and just contracted the 1 form into the bivector.
So would you say
Yeah.
holomorphic would be complex?
Yeah, like complex analytic. Yeah. Yeah. Yeah, so they have like they all look like CN locally, and the transition maps are like analytic. So if you're holomorphic symplectic, then this anchor map that we had defining this cotangent Lie algebroid is now an isomorphism of Lie algebroids. So T star X is the same thing as T, and we know that T is integrated, or rather is the Lie algebroid of the fundamental groupoid. And we already calculated what the Picard group of the fundamental groupoid is. It's just the outer automorphism group. So this is the Picard group of a holomorphic symplectic manifold. Okay. On the other extreme, if your bivector is a non-degenerate, but is as degenerate as it possibly could be, So we just have the zero Poisson structure. Then this is integrated by the holomorphic symplectic manifold, which is just the cotangent bundle of X. Okay. So this is a Lie groupoid, a holomorphic symplectic Lie groupoid. So it's a holomorphic symplectic manifold because it's the cotangent bundle of a complex manifold. And you can ask what the groupoid structure is. And that's just given by addition in the fibers of the vector bundle. Okay, so this is a holomorphic symplectic Lie groupoid, and it integrates the zero Poisson structure. So we can ask what is its Picard group, and its Picard one group is the following semi-direct product of the group of automorphisms of X with this subspace of the second de Rham cohomology of X. It's the first step in this thing called the Hodge filtration. So if you're a Kähler manifold, then this is just H11 plus H20. Okay, so why is this true? Given something in here, so an automorphism and a two form, or a cohomology class here, we can produce the following Morita equivalence. So the bibundle, the Morita equivalence as a manifold is just going to be T star X again. Okay. But what I'm going to do is I'm going to change the symplectic form. This is a two form, and I can change it by pulling back this two form V in the Picard group, which lives down here. I'll pull it back using this pi map. And then this is again a holomorphic symplectic manifold. So that's good. And then I can use the automorphism to just deform this one, this projection map onto the base. Then you can check that this is going to be a holomorphic symplectic bi-principal bundle. Okay, and if you take phi to be the identity map here, this is something which was studied before. Donaldson studied these things. They're called twisted cotangent bundles. Okay, so here's the main theorem, which is that if you have a compact holomorphic Poisson manifold, then its Picard one group, at least the connected component of the identity of this thing, is a finite dimensional complex Lie group. So what this means is, well, if finite dimensional complex Lie groups have Lie algebras, so this means that not only do we have the Picard Lie group, but we have the Picard Lie algebra, which is just the Lie algebra of this Lie group. So these are two finite dimensional things which you can canonically associate to any compact holomorphic Poisson manifold. And this is maybe somewhat surprising, or not surprising, but special to the holomorphic setting. If you look at like symplectic groupoids in the category of just smooth manifolds, where we don't require things that are complex analytic, then these Picard groups are almost always infinite dimensional. So this is another reason to only do complex geometry. Okay, so an example of Picard Lie algebra. If we have the zero Poisson structure, we just saw that pick one, this was aught X, semi-direct, this F1 H2 de Rham. So its Lie algebra is just going to be the Lie algebra of holomorphic vector fields acting on this representation via the Lie derivative, which is actually a trivial action on cohomology, but there's an example. Okay, and so for the remainder of the talk, I want to just talk about some of the things which go into proving this theorem. We have this crazy notion of this bibundle, which is like a ton of data. Somehow we can compose these things, they form a group. And somehow I'm claiming that if you take this equivalence relation, this is actually a finite dimensional complex Lie group. So what we need is this notion of a bisection. So remember, if you have a vector bundle, like E to X, pi, a section of the vector bundle is just a map here, which post-composes with pi to be the identity. Okay. So a bisection of a Lie groupoid now is going to be some map from the base into the arrows, which Poisson composes with the source map to be the identity, but it's too much to ask that it composes with the target map to be the identity. I'm just going to ask that this composition is some diffeomorphism of X. Okay. Now, I'll call this Lagrangian if when I pull back the symplectic form, I get 0. And it's going to be static if it's actually a section for both source and target. Okay. So like in pictures, if this is the groupoid G, there's the identity living inside of it. You should think of a bisection as something which like looks like the identity objects sitting inside of it. But I mean, it isn't exactly the identity objects. It's sort of like a deformation of the identity, or not identity. It's like a deformation of the objects sitting inside the arrows of the category. Okay, and these things form a group. You can compose them. And I'll call the subgroup of static Lagrangian bisections LS bis. Okay. So then the last group that we'll need is this group, which Francis calls pic B. So this is pairs P gamma, where P is one of these holomorphic symplectic Morita autoequivalences, and then gamma is a bisection of P. All right. Now with this, we have the following result, which is if G omega integrates X sigma, which is a holomorphic Poisson manifold, then we have a long exact sequence of groups. So this pic B group is going to map to the Picard, where if I have Morita autoequivalence and a bisection, then I can just forget about the bisection and send it to the class of that Morita equivalence. Okay. So this is not a surjective map, but if you restrict this to the connected component of the identity, then it actually is surjective. The kernel of this map is another group. It's the group of bisections of the groupoid. And then the map from here into here isn't actually, okay, so the kernel of this isn't exactly bis. It sits in this long exact sequence. I don't know if it's proper actually to call this a long exact sequence. Maybe that sort of implies that it goes on forever. It's not a short exact sequence. It's an exact sequence. Okay, so here's our exact sequence. And if X is a compact manifold, then you can actually turn these three groups here into infinite dimensional Lie groups. So even if we're working in the complex analytic world, these three things here are all infinite dimensional, and you can give them Lie group structures modeled on these types of Fréchet spaces called ILB spaces. And because of that, we can differentiate them as Lie groups, and we'll get an exact sequence of Lie algebras. Okay.
So X is a Fréchet space.
X is a manifold. It's a compact, it's like projective space.
Okay.
And then these are groups that I build out of X and holomorphic Poisson structure on X. They're like spaces of, well, their Lie algebras are going to be spaces of smooth sections of finite dimensional vector bundles on these manifolds. Which means that these are actually infinite dimensional Lie groups. Okay, so I have not claimed that this is a Lie group. That's what we want to prove. But that's hard. It's hard to take quotes of infinite dimensional Lie groups. There's a lot of analysis which goes into it. But what's a bit easier is taking quotients of infinite dimensional Lie algebras. So let's do that first. So if you have a compact holomorphic Poisson manifold, then this Picard Lie algebra, which was just there, is actually a finite dimensional complex Lie algebra. Okay. So,
You figured out how to shut it off.
no,
Sorry.
I tapped my water bottle and
Okay.
then that happened. Okay, cool. So, yeah, let's prove this. So I need to tell you three things. I need to tell you why this thing is a Lie algebra. I need to tell you why it's finite. And I need to tell you what the complex structure on it is. Okay, so it is a quotient of this thing which I called pick B. And then there was a map from real one forms into this pick B. And then there was something else here, but that doesn't matter. Okay, so this pick B, you can compute it to be the following thing. It's all 1, 0 vector fields on X and closed two forms, which have to satisfy a bunch of relations, which I wrote down here. These relations are actually really interesting. They say some interesting things, but it's not super important. But what is important is that if I have two things here, like V beta and W gamma, say, then I can define your Lie bracket to just be the Lie bracket of the vector field part. And then I can act on the forms using the vector field via Lie derivative. Okay. So this is the Lie algebra structure on this pick B group. And the image of this inside of here is an ideal. So pick inherits the Lie algebra structure from this formula. Okay. Okay, so this first bullet is what I just said. Now, why is it finite dimensional? So this is a bit involved, maybe, but we had this anchor map which went from the cotangent to the tangent. And this is going to induce a map from all differential forms to all wedges of vector fields. And this is a morphism of complexes of sheaves or vector bundles. But what you can do is, in particular, these are both chain complexes. So you can form the cone of this morphism of cochain complexes. And this is another cochain complex, which I call C sigma. And you can check that this Picard Lie algebra, these relations, I went back a page, maybe that was a bad idea. Okay, these relations are exactly saying that you are a one cocycle in this cochain complex. So this Picard Lie algebra can be identified with this first hypercohomology group of this complex of sheaves, which because this is a like complex of coherent sheaves on a compact manifold, this is inherently finite dimensional. Okay, so this is why working in the holomorphic category, or how working in the holomorphic category is giving us finite dimensionality. Yeah. Okay. Okay, so the last thing is the complex structure. And this is a decent amount more involved, but basically what is happening is on this pick B thing, together with the one forms, you can define this thing called a homotopy complex structure. So it's not actually a complex structure. It doesn't square to minus the identity, but it squares to minus the identity up to some prescribed chain homotopy. And when you pass to cohomology, that failure up to homotopy is going to disappear, and you actually get something which squares to minus the identity. So because the thing that you've defined this homotopy complex structure on, its zeroth cohomology group is pick. The homotopy complex structure on this thing, when I take cohomology, becomes a genuine complex structure on here. Yeah, so these ideas here are due to Francis. But it's a bit too much to say here for the one slide. Okay, so that's the proof. The Picard Lie algebra for a compact manifold holomorphic is a finite dimensional complex Lie algebra. And then I claim that this means that the Picard one group, at least its identity component, because that's where we have the Lie algebra, is a finite dimensional complex Lie group. So how we prove this is we saw before that this is an exact sequence of groups. Now what you need to, and I also claimed that the first three things in the sequence are these infinite dimensional Lie groups. Now what you need to do is prove that it is an exact sequence of infinite dimensional Lie groups. In particular, that if I take the quotient of this by the image of this, the result is still a Lie group. So you need some sort of way to take quotients of infinite dimensional Lie groups. And it just happens due to certain niceness things like having elliptic operators floating around that you can use this result of Hideki Omori, which he calls the Frobenius theorem, to prove that this quotient of infinite dimensional Lie groups is again a Lie group. And you can identify this Lie group's Lie algebra with this pick, which we saw before. And we know that this thing is a finite dimensional complex Lie algebra, which means that this pick one is a finite dimensional complex Lie group. So the hard part here is actually showing that this quotient is again a Lie group. But once it is, because you know it's Lie algebra, you know that it's complex and it's finite dimensional. Okay. Cool. Okay. So let me just say one general tool we have for studying the Picard group. So I gave you some fact about it. It's some finite dimensional complex Lie group. How do you actually construct elements in it? So what you can do is if you have this thing called a Poisson module, which is just a line bundle over top of your Poisson manifold, but it's a line bundle with a Poisson structure on it as well. So the total space of this line bundle also carries a holomorphic Poisson structure. Okay. All right, so here's my map of the line bundle over the space with their Poisson structures. And what you can do is you can integrate this total space as a holomorphic Poisson manifold to its holomorphic symplectic Lie groupoid. Okay. It's the total space of a line bundle, but it's a holomorphic Poisson manifold, so you can try to integrate it. All right, so let's assume that we can do that. Now there's a C star action on the fibers of this line bundle, just by like rotation. And that will induce a C star action on the associated groupoid. And the associated action on the groupoid actually becomes Hamiltonian. So there's a moment map for this Hamiltonian group action to C. Now, C is a group under addition, right? And groups are groupoids. And this mu is actually a groupoid map. So what that means is that if I do Hamiltonian reduction at 0, then I'm going to get a groupoid back. And what is that groupoid? It's the groupoid integrating X itself. Okay. So we started by integrating the line bundle with its holomorphic Poisson structure. And if we do Hamiltonian reduction at 0, we get the groupoid integrating the thing on the base. All right. But you can also reduce at non-zero values. And if you do that, you're not going to get a groupoid anymore. But what you're going to get is actually an element of pick. You're going to get some bibundle. And the reason for this is just because 0 plus lambda is lambda. So the thing which I get the preimage of 0 or reduction at 0 is going to receive an action from the thing. Sorry, if I reduce at lambda, it's going to receive an action from the thing that I got by reducing at 0. Okay. So you can do this for any lambda in C. So I'm actually getting a whole family of bibundles by reducing at these different values of lambda. So what this is saying is if you ever have one of these line bundles with a holomorphic Poisson structure, call them Poisson modules, then this is actually giving you a one parameter subgroup in this Picard group. Yeah. Okay, that's everything I wanted to say. Thank you for your attention.